Hello everybody, welcome to another episode of Math-221. So today we are going to cover section 8.3, which is equivalence relations. Okay, so first we need to review what a partition is. So recall that a partition of a set A is a finite or infinite collection of non-empty mutually disjoint subsets whose union is A. Okay, so that mutually disjoint part means none of the subsets overlap. That's what that means. So for example here, these subsets 1, 2, 3, 4, and 5, 6, those are a partition of the set 1, 2, 3, 4, 5, 6. So they cover everything that's in the larger set and they don't overlap with each other at all. And then visually, if you want to picture it, so this whole big set here, this would be A. And then we've partitioned it into smaller subsets A1, A2, A3, A4, A5, and A6, which do not overlap. So this part right here, that's telling you that they don't overlap, so their overlap is empty. So the sets in the partition, your book didn't mention this, but they're sometimes called parts, and it's useful to have a word for them to talk about them. So for example, 1, 2 is a part of the partition of 1, 2, 3, 4, and 5, 6. Okay, so we just finished covering relations in the last two sections. So relations are actually highly related to partitions. And one of the ways that they're related is the following. So if you have a partition of a set A, the relation induced by the partition R is defined on A as follows. So for all xy, which are elements of A, we say that x is related to y by R, if and only if there is a subset AI of the partition such that both x and y are in AI. So in other words, x and y are in. That is not saying x and y, is it x? Sorry. And y are in the same part, if you want to use that word that I gave you on the last slide. Okay, so let me just do like a really quick example here so you get the idea. So for example, we saw before that 1, 2, 3, 4, and 5, 6 is a partition of the set 1, 2, 3, 4, 5, 6. So if we define R in the way that it's defined in this definition, then we would say that 1 is related to 2 by R, and for example 3 is related to 4 by R, but 1 would not be related to 3, for example, because those are not in the same part. So that is how the relation induced by the partition works. Okay, so now let's talk about some properties of this relation induced by the partition that we just defined. So the first thing we have here is Theorem 8.3.1. Let A be a set with a partition, and let R be the relation induced by the partition. Then R is reflexive, symmetric, and transitive. So those are the three properties we covered in the last section. So I'm just going to do a little sketch of the proof here. So by a proof sketch, what I mean is something that is not quite as formal as a proof, but it gives you most of the important ideas of the proof. So this is not very hard to prove at all. It's quite natural. So for the reflexive part, if you let A be an element of the set A, then A has to be in the same partition, the same part of the partition as itself. That's pretty obvious. So that shows that the relation would be reflexive. And then if you consider two elements A and B in the set A, if A is in the same part of the partition as B, then B is in the same part of the partition as A. That's pretty natural, I think. So that one shows that the relation would be symmetric, and this one was showing reflexive. Okay, and then for the last statement here, let A, B, and C be elements of the set A. If A is in the same part of the partition as B, so in other words, A is related to B, and B is in the same part of the partition as C, so in other words, B is related to C, then A is in the same part of the partition as C. Hopefully you agree that's a pretty natural thing to see there. So that shows that the relation is transitive. So those are the important ideas of how you would prove this theorem. Okay, and now we're coming to the definition of an equivalence relation, which is what this section is all about. So let A be a set and let R be a relation on A. Then we say that R is an equivalence relation if and only if R is reflexive, symmetric, and transitive. So it must have all three of those properties. And then it will be an equivalence relation. So the idea behind this is that equivalence relations they share similar qualities as the equals relation, so to equality. So if you think about equality and the properties that equality has, equality is reflexive, so everything equals itself. Equality is symmetric. So if A equals B, then B equals A. And equality finally is transitive. In other words, if A equals B and B equals C, then A equals C. So these are the natural properties of equality, and you've known about them for a long time and probably not thought too deeply about them. But there are a lot of other relations that also share these properties, which can be quite useful. Okay, so now let's talk about the equivalence classes of an equivalence relation. So if you have a set A and R is an equivalence relation on A, then for each element little a in big A, the equivalence class of little a, which is denoted like this, it's bracket A, that is called the class of A for short, or you can call it the equivalence class of A for long, is the set of all elements x in A such that x is related to A by R. And so to say that symbolically, we say bracket A is the set of all little x in big A such that x is related to A by R. And then if you just want to shorten that up, you can say for all x in A, x is an element of bracket A if and only if x is related to A. So if you find that x is related to A, then you get that x must be in the equivalence class of A or in bracket A. And if you find that x is in bracket A, then that means that x is related to A. And of course, if we're talking about an equivalence relation, then this is symmetric, so you would also be able to say that A is related to X, if you like. Okay, so let's just look at a quick example to make sure we've got the idea of how the equivalence classes work. So here we have the set A, which is little a, b, c, and d, and then the relation here is given by these ordered pairs. So for example, this one here means that A is related to A, and so on and so forth. So we want to find the distinct equivalence classes of R. So I think what I'm going to do is I'm just going to go through all of the elements of A, and I'll just find out what their equivalence class is. So I'm just going to go through and find these 4 things. Okay, so remember this is going to be all of the elements that are related to A, and because this is an equivalence relation, they could be related in either order. Okay, so but I think A is only in this first ordered pair here. So this is just going to be A and nothing else. Okay, and then for B, what is B related to? So B is related to itself, and it's also related to D, and here's the other order in which it's related to D right there. So these two are going to give me, or those 3 I suppose, are going to give me B and then D. Okay, and then C, what is C related to? Let me switch to a different color, this might be getting confusing. So I think C is only related to itself, so that's going to give me just C there. And then finally for D, D is related to itself, and then D is also related to B in both orders. It is an equivalence relation, so of course it has to be in both orders in those ordered pairs. Okay, So that for the equivalence class of D is going to give me D and then also B. So actually, these two, let me switch colors again. So these two right here, these are the same. So the distinct equivalence classes, sorry if you guys can hear my cat meowing, he's very insistent about what he wants. So the distinct equivalence classes are bracket A, which is just A, and then bracket B, which is equal to bracket D, which consists of just B and D. And then finally bracket C, which is just C by itself. Okay, so let's look at a homework problem. Okay, so here's your homework problem, and it's almost exactly like what I just did, so go ahead and give that a try, and check the answer in the back of the book. Okay, so let's look at this Lemma 8.3.2. So just to remind you, a lemma is basically the same as a theorem, but usually a lemma is something that you write in order to help you prove a bigger theorem. But this is useful in its own right. So Lemma 8.3.2, suppose A is a set, R is an equivalence relation on A, and A and B are elements of A. If A is related to B by R, then the equivalence class of A is equal to the equivalence class of B, or bracket A is equal to bracket B. So this is interesting, and I think we had noticed this on the last couple of problems. For example, on the example I did, we had that B and D were related, and we found that the equivalence class of B was equal to the equivalence class of D. So let me show you with this little proof sketch here why this is actually the case. Okay, so suppose that you have X is an element of the equivalence class of A. Then that means that X is related to A by the equivalence relation. So since A is related to B and R is transitive, so look at what we have here. We have this one, X is related to A, we have A is related to B, and we have that R is transitive. So then we can transit all the way from X over to B and say that X is related to B. So that means if X is related to B, then X is in the equivalence class of B as well. So we started with X being in the equivalence class of A, and then we showed that it also had to be in the equivalence class of B. That means that the equivalence class of A is a subset of the equivalence class of B. And now the other way around, we suppose that X is an element of the equivalence class of B. That means that X is related to B by R. And so since we know that A is related to B, because that was up here, that was this if statement here, and R is symmetric, that means that we can switch that around and say that B is also related to A. And now look at what we have. We have X is related to B, B is related to A, and R is transitive because it's an equivalence relation. So that means that we can go all the way from X over to A and say that X is related to A. So if X is related to A, that means X is in the equivalence class of A. And so we started by saying that X was in the equivalence class of B, and we found that X is in the equivalence class of A. That means that the equivalence class of B is a subset of the equivalence class of A. And so since we have these two subset relationships here, that means that the equivalence class of B is actually equal to the equivalence class of A. So that is how that proof works. And now let's look at another lemma. Okay, so lemma 8.3.3. So if A is a set, R is an equivalence relation on A, and A and B are elements of A, then you have one of the following. Either A and B are disjoint, so their intersection is empty, they have no elements in common, or the equivalence class of A is equal to the equivalence class of B. So those are the only two possibilities for two equivalence classes. They're either disjoint or they are the same. So here's how we could go about proving this. So if we have two elements, A and B, in our set A, then there's only two things that can happen as far as the relation. Either they're related to each other, which is this one, or they're not related to each other. So one of those two must be the case. So let's look at those separately. So in case one, we have that A is related to B. And so in that case, we can use the last lemma on the last slide to say that since A is related to B, that means the equivalence class of A is equal to the equivalence class of B. Okay, so that's case 1. And then in case 2, so in case 2, we have that A is not related to B. So we can prove that the overlap or the intersection of the equivalence class of A and B is empty by the method of proof by contradiction. So remember, that's what we'd been using to prove that sets were empty in the previous chapter. So suppose that there is some element X that is in the overlap or the intersection of these two equivalence classes. Then that would mean X is in the equivalence class of A and X is in the equivalence class of B. So, because it's in both of those equivalence classes, that would mean that X is related to A and X is related to B. Well, since R is symmetric, we could also swap the first one of those around and say that A is related to X. And then, since A is related to X and X is related to B and R is transitive, then we can say that A is related to B. Okay, so that's using these two and the transitive property. And that's a contradiction because we started out in this case by saying that A was not related to B. So we got a contradiction. That means our supposition was wrong. So we supposed that there was some X that was in the intersection of congruence class of A and B, equivalence class of A and B. So if that was wrong, then there is no element X in the intersection of these equivalence classes, and so that intersection must be empty. Okay. All right, so now we're prepared with those two lemmas to prove the following. Theorem 8.3.4. So this is about the partition induced by an equivalence relation. So if A is a set and R is an equivalence relation on A, then the distinct equivalence classes of R form a partition of A. That is, the union of the equivalence classes is all of A, and the intersection of any two distinct classes is empty. So the proof sketch here is pretty simple. So since we know that every element little a in big A is in an equivalence class that's just its own equivalence class, that means that the union of all of the equivalence classes will be A, because every element in A will be contained in at least one of them. And then, so that's one thing that you need for a partition. And then the other thing that you need for a partition is that you need that the parts of the partition are disjoint. And we know that from the last two lemmas. Every pair of equivalence classes, bracket A, bracket B, they're either the same or they are disjoint. Okay? So that means that the equivalence classes are mutually disjoint. So this is interesting because we started out by talking about how a partition gives rise to an equivalence relation, and now we're saying that equivalence relations actually give rise to partitions. So you really can think of partitions and equivalence relations. It's like two different views of the same thing. If you have a partition, then you have an equivalence relation. If you have an equivalence relation, then you have a partition. So they're kind of the same thing in that sense. Okay, one last thing to talk about here before we do an example is representatives of equivalence classes. So suppose R is an equivalence relation on a set A and S is an equivalence class of R. Then a representative of the class S is any element A such that angle bracket of A equals S. And another way to say this would be or such that A is an element of S. Since if A is an element of S, then angle bracket, or sorry, not angle bracket, then, let me just write it out. So since if A is in S, then bracket A, the equivalence class of A, will actually be equal to S. Okay. So we can represent these equivalence classes by any of the elements that are in them. Let me just give you another example. I don't know if this is making sense to you or not. So if S was, let's say, A, B, C, then we can represent S as bracket A, or as bracket B, or as bracket C. All of those will be equal to S. So we can use any of those three elements to write down the name of the equivalence class. Okay, so let's look at this example here. So in these next few problems, 3 through 14, the relation R is an equivalence relation on the set A. Find the distinct equivalence classes of R. So our set A here is all the integers from -5 up through 5. And then the relation R is defined on A as follows. for all m and n in the integers, m is related to n by r, if and only if 3 divides m squared minus n squared. Okay, so what I have to do here is just go through all of these elements of the set A and figure out what all is related to them. So I'm just going to start with -5. So I know that -5, of course, it's in its own equivalence class because this is an equivalence relation, and also because -5 squared minus -5 squared is 0, and 3 divides that. So let's figure out what else would be related to -5. So I think -4 will also be in there, and just to justify that, that's because 3 does divide -5 squared minus -4 squared, because that would be 25 minus 16, which would be 9. Okay, let's see, what else would be in there? Will -3 be in there? So I think -3 is not in there, because then I'd be looking at 25 minus 9, which would be 16, and that's not divisible by 3. Okay, -2, so if I do 25 minus 4, I get 21, which is divisible by 3. So I think -2 is in there, and I'll just put a little sidebar here. That's because 3 divides -5 squared minus -2 squared, because that would be 3 divides 21. Okay, what else? -1, if I do 25 minus 1, I get 24, which is divisible by 3, and I think I'm not going to list the rest of the reasons, but that's why that one is there. 0, no, because 25 minus 0 would be 25, which is not divisible by 3. And then as I'm looking at these positive ones, I think I'm going to get the same numbers that I got when I was looking at the negative ones, because we're squaring, and so the sign is not going to matter. So here I'm just going to get 1, 2, 4, and also 5 for the same reasons that I got -1, -2, -4, and -5. Okay, so that is the equivalence class of -5. I'll just put, sort of etc. for the rest of them, the reasons there, and you can fill them in yourself if you want. So that means that this is also the equivalence class of -4, this is also the equivalence class of -2, this is also the equivalence class of -1, and so on and so forth for all of these elements that are in there. They all have the same equivalence class, because remember, two equivalence classes are either exactly the same or they have no overlap at all. So if anything is in an equivalence class, then it is the same equivalence class for that element. Okay, so what are the elements that we did not cover here? I think the only ones we skipped were 3 and -3, and I do believe those should definitely be in the same equivalence class. Because you'll get 9 when you square both of them, and so 9 minus 9 is 0, which is divisible by 3. So that's also the equivalence class of -3. Okay, so in this case there were only 2 distinct equivalence classes, and I've written out both of them. Okay, so here is your homework problem, and it is extremely similar to the last one, but you're doing divisibility by 4 this time. So go ahead and give this a try and look up the answer in the back of the book. Okay, so now I want to talk about a particular equivalence relation that comes up in a lot of different contexts in math and computer science, and this is the congruence modulo n relation. So let m and n be integers, and let d be a positive integer. We say that m is congruent to n modulo d, and we write this, which I would just read aloud as m is congruent to n modulo d, if and only if d divides m minus n. And symbolically you can write it like this: m is congruent to n modulo d, if and only if d divides m minus n. So this is actually an equivalence relation, and I want to say just a little bit more about it. So there's actually another way that you can define this particular equivalence relation. So we already talked about the fact that m is congruent to n modulo d. That means that d divides m minus n. Another way you can actually check that is if you just check that m mod d equals n mod d. So you have to be a little bit careful here, because I'm using 2 different notations that both say mod d, And you need to distinguish this one that's in parentheses over here with this little 3-bar equivalence thing here. Distinguish that from this mod D that's over here without parentheses, and it just has a regular equal sign here. So let me tell you what the difference is between these two notations. So M is congruent to N mod D. That notation there is a statement. So that is stating that M and N, either that D divides M minus N or that M and N have the same remainder after long division by D. Whereas this N mod D, that is an operation, just like the plus or the minus or the division or the multiplication operation. It's an operation that returns the remainder of N after long division by D. Okay, so this, we're using mod D for both of them, but they actually mean slightly different things. Okay, but the things that they mean are closely enough related that is why we use the same mod D in both places. But here in this statement right here, this is saying that the remainder of M after long division by D will be the same as the remainder of N after long division by D. And this over here is basically equivalent, but it's just stating it with a different notation. So this little 3 bars thing is equivalence, and then this mod D here is in parentheses. And then both of those are equivalent to saying that D divides M minus N. Since if you subtract two things that have the same remainder, the remainders will cancel out, and then you'll have something that's divisible by D. Okay, let's try doing some problems with this concept. Okay, so let's go ahead and do this example here. It's pretty simple. It's just true or false to make sure that you understand how the notation is being used. So let's go ahead and I'll do part B here. So I want to know if 4 is congruent to negative 5 mod 7. So what I'm going to do is I'm just going to check whether or not 7 divides 4 minus negative 5. So that's equivalent to checking whether 7 divides 9, but it does not. That's false. So 4 and negative 5 are not congruent modulo 7. All right, let's check part C here. So I'm checking whether or not negative 2 is congruent to negative 8 mod 3. Okay, so I'm just going to check whether or not 3 divides negative 2 minus negative 8. And I think in this case it's going to be true because 3 does divide 6. So this is true. Okay, so negative 2 and negative 8 are congruent mod 3. And finally part D here. So is negative 6 congruent to 22 mod 2? Okay, so what I want to know is does 2 divide negative 6 minus 22? I should have put questions on all these since I wasn't sure if they were true. Okay, so I'm checking whether or not 2 divides, let's see, what is that, 16? And that is true. Okay, so the answer there was yes, true, it does divide 16. So negative 6 and 22 are congruent modulo 2. Okay, so go ahead and do part A there and see what you get, and you can check your answer in the back of the book. Okay, so let's look at this problem here, number 16. Let R be the relation of congruence modulo 7. Which of the following equivalence classes are equal? Okay, so what you want to note here is that since R is an equivalence relation, if, for example, A is related to B by R, then that means the congruence classes of A and B are equal, or the equivalence classes of A and B are equal. We proved that. I think that was one of the lemmas that we did. So all we really need to check is if these pairs of elements are related to each other. So we're doing congruence modulo 7, so we can just check by subtracting and then seeing if the remainder is divisible, or sorry, by subtracting and seeing if the result is divisible by 7. Or you can do that thing where you get the remainder from long division. Some of these are negative, so I don't think we really talked about how to do long division on negative numbers. So I'm just going to subtract and then see if the result is divisible by 7. So let's just check 35 and 3. So I think 7 does not divide 35 minus 3. So that would mean that 35's equivalence class is not the same one as 3. Let's see. We could also check, let's see, I think 7 does divide 35 minus negative 7, because that would be 42. So those two will have the same congruence class or equivalence class. Okay, I can check some others. Let's see. So 35 and let's see, what else would go in 35s? So I don't think 12 is going to go. 0, I think 7 will divide 35 minus 0, so that will be the same. And then I think that's the only ones that work for 35. I mean, you can check them all one by one, but I think it's not too hard to do some of it in your head. Okay, so let's see. So what else would be in the congruence class of 3? So we already established that the congruence class or the equivalence class of 3 is not the same as 35. So I also don't need to check that it's whether or not it's the same as negative 7 or as the equivalence class of 0, because I know those are the same as the equivalence class of 35. So basically, like, to summarize what I have so far, I have that these 3 are equal. So, okay, so let me look. So that basically takes care of those 3. So let me look at some of the others, like 3 and 12. So I think 7 does not divide 12 minus 3. So congruence class of 3 is not going to be the same as the congruence class of 12. Sorry, I keep saying congruence class. That is actually a thing. They just didn't define it in the book, but that is a word that exists. I'm not just making up words. Okay, I can compare 3 with, let's see, what else is there? Okay, 7 does divide 17 minus 3. Okay, so we found that one. Those two will be the same. Did I check everything else against 3? I think everything but negative 2, but 7 is not going to divide 3 minus negative 2. So those will not be the same. Okay, so far what we have is congruence class of 3 is the same as congruence class of 17, but none of the others are the same as those. Okay, so I did that one, All right, so I have left 12 and negative 2, and I think 12 and negative 2 are not going to be congruent because 7 is not going to divide 12. Oh, wait a minute, yes it does. What am I saying? 12 minus negative 2 is 14. So yeah, okay, those are the same. So the last the last identical ones that I get are that the equivalence class of 12 is the same as the equivalence class of negative 2. Okay, so that's it. So go ahead and pause the video and do part A and see what you get. Okay, so we're backing up a little bit. I kind of did some of the problems out of order, but this is number 6, and in this problem, the relation R is an equivalence relation on the set A, and we are to find the distinct equivalence classes of R. So we're doing the numbers in A from -4 up through 5, and then R is defined in the following manner. For all x, y in A, x is related to y by R if and only if 3 divides x minus y. So this is basically, this is congruence mod 3, is basically what that is. Okay, so let's just check which of these are congruent mod 3. So I'm going to start with -4. So what would be congruent to -4 mod 3? So let's see, if I do -4 minus -3, then I get -1, so that's not divisible by 3. If I do -4 minus -2, that'll be -2, that's not divisible by 3. So the next one that I get, I think, after -4 itself is -1. So -4 minus -3 is -3, which is divisible by 3. And then after that, you can keep going in the same manner, and the next one that you get is, I believe, 2. So -4 minus 2 is -6, and that is divisible by 3. And then after that, I believe you get 5. So -4 minus 5 is -9, and that's divisible by 3. So what's interesting actually about these congruence classes, and I haven't mentioned this till now, but we could have used it in the previous problems, is that when you're writing out the elements of one of these equivalence classes for the congruence mod n relationship, you can always get from one element to the next in there by just adding the modulus, or the n value, in other words. Do you see how that works? So I went from -4, and then the next one was -1, and then the next one was 2, and the next one was 5. And those are all spaced 3 apart. And of course, that's not an accident at all. It's because those are the numbers that are going to have the same remainder after long division by 3. And then so when you subtract those numbers, the remainders will cancel out, and you'll get something that's divisible by 3. I hope that makes sense to you. Okay, so the next equivalence class, I could do -3's equivalence class. So that's going to contain -3, and then following on the same pattern, the next one will be 0, and then 3, and then that'll be the last one since we stopped at 5. But you could keep going 6, 9, 12, etc. if we had all of the integers. Okay, and then the next one will be -2. And so that's going to contain -2, and then adding 3, I get 1, and then if I add 3 again, I get 4. And I believe that's it. So this covers all the values of A, and these are the only 3 distinct equivalence classes. The rest of them are equal to these. You know, like for example, this is the same as the equivalence class of 1, which is the same as the equivalence class of 4, and so on and so forth. You could do that for all of these. And so on and so forth. Okay, so here is a homework problem that is very similar. So you've got the numbers from 1 to 20, and your modulus here is 4. But other than that, it's the same problem. So go ahead and give this a try and check your answers in the back of the book. Okay, so now let's do a little bit different type of equivalence relation that's not about modulo n. So in these problems from 19 to 31, we have to first prove that the relation is an equivalence relation. So in other words, prove that it is reflexive, symmetric, and transitive. And then secondly, describe the distinct equivalence classes of each relation, which is what we've been doing before. Okay, so I'm going to do part B here. So part B, or rather in the whole of 19, A is the set of all students at your college. And then in part B, S is the relation defined on A as follows. For all x, y in A, x is related to y by S if and only if x is the same age as y. So for every 2 college students, we say that those college students are related by S if and only if they're the same age. Okay, so let's go ahead and try proving that this is an equivalence relation. So proof that S is an equivalence relation. So this is going to involve 3 things. So first of all, reflexive. We need to prove that it's reflexive. So to prove that a relation is reflexive, you let, I'll just call it, I don't know, x, let x be an element of A. So I need to show that x is related to itself by S. So here's my goal statement. We will show x is related by S to x. Okay, so how are we going to do that? Well, I just need to have that x is the same age as x, which of course is always true. Remember, x is a student, so then x is the same age as him or herself. So x is related to itself by S. Okay, so that means that S is reflexive. So S is reflexive. All right, that's not too bad. Let's do symmetric. So I think this one is equally not very hard. So symmetric. So let x and y be elements of A, so they are students at Susquehanna. Then we need to show the following, that if x is related, oops, it's not an R. If x is related by s to y, then y is related by s to x. Okay, so we're trying to show an if-then statement. So whenever you're proving an if-then statement, usually you just assume the if part and then show the if part. Sorry, show the then part. I think I just said diff, which is not a word. Okay, so we're going to assume that x is related by s to y. All right, so what does that tell us? What do we get for that assumption? Well, that means, so the definition of this s relation is that x is the same age as y. Okay, well, if x is the same age as y, then y is the same age as x. So that is, I've basically just swapped the order of them, so that tells me that y is related to x by s. Okay, so that's all you need to show that s is symmetric. Okay, and finally let's do transitive. So transitive. Okay, so for this one we need 3 elements or 3 students. So let x, y, and z be elements of A, or in other words, they are Susquehanna students. So here's what we're going to show for transitive. This is just the definition of transitive. We will show that if x is related to y by s and y is related to z by s, then x is related to z by s. And I think it should not be very hard to see why this is true. So again, we're proving an if-then statement, so we're going to assume the if part. So assume x is related to y by s and y is related to z by s. Okay, so we made the assumption of the if part. What do we gain by that assumption? What does that assumption tell us? So that tells us that x is, since x is related to y by s, then x is the same age as y. And since we had y is related to z, that also tells us that y is the same age as z. Okay, well, if x is the same age as y and y is the same age as z, then that means x is the same age as z. So x is related to z by s. Okay, so s is transitive. All right, so we proved that S is an equivalence relation. Just have to prove those 3 properties. So on the next slide, I will do the part 2 where I describe the distinct equivalence classes of each relation. Okay, so now let's talk about 19b, part 2. So part 2 is to describe the distinct equivalence classes of each relation. So the equivalence classes for this relation here, the same age relation, is just going to be one class for each age. I mean, I assume by age they're talking about 18-year-olds, 19-year-olds, etc. If I meant something different, then I am not sure the first part of this problem would have gone well. So the equivalence classes are just going to be, so I don't actually know how young the youngest person at SU is because there are some high schoolers that take classes. So I'm just going to put a little ... and I'm not really sure where it kind of starts at. So I'll say maybe like the 17-year-olds should go there. And then the 18-year-olds just abbreviate it like that. The 19-year-olds, the 20-year-olds, and then I'll just put a dot, 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 because I don't really know where it ends at either. We might have some older people, I don't know. But yeah, those would be the equivalence classes. All right, so go ahead and pause the video and try part A, do the part 1, prove it's an equivalence relation, and also do part 2, describe the equivalence classes, and check your answer in the back of the book. Okay, so let's look at this next example here. So this one is about congruence mod 4 in this case, and we're calling it F. I guess F stands for 4. So we're going to prove that the relation is an equivalence relation, and then we're going to describe the distinct equivalence classes. Okay, so let's go ahead and try this. So proof that F is an equivalence relation. Okay, so first thing I need to do, so this is part 1. So first thing I need to do is show that F is reflexive. Okay, so for this, I just need to take an element of the set that the relation is on. So I'm going to say let x be in, I guess we're working with the integers here. So let x be in the integers. And what I need to do here, my goal is we will show that x is related to itself. So x, f, x. Okay, so that's our goal. So the way I'm going to do this, I'm going to need to show that 4 divides x minus x. So let's see, what can I say? Then x minus x is 0. So 4 divides x minus x. So x is related to itself by f. Okay, so that means that f is reflexive. Usually reflexive is not very hard to show. It's usually the easiest one. Okay, now let's do symmetric. Okay, so here I need 2 elements. I'll just call them x and y. Okay, so then what we're going to show, our goal, just the definition of being symmetric, is we will show that if x is related by f to y, then it goes the other way around. Y is, sorry, I don't like that y. Then y is related to x by f in the other order, like that. Okay, so we're trying to prove an if-then statement. So assume that x is related by f to y. Okay, what do we gain by that assumption? What does that tell us? So our definition of this is the following. Then 4 divides m minus n. Okay, so at this point there's a couple of routes you could go. You could just say directly that 4 must also divide n minus m, because n minus m is negative m minus n. Or you could use the definition of divisibility. So I think I'll go that route just to make it a little more detailed. So what does it mean that 4 divides m minus n? That means there exists some integer, which I'm going to call q, you can call it whatever you want, such that m minus n equals 4q. So that's what it means for 4 to divide m minus n. Okay, now let's think about what we're trying to show. Remember, we're trying to show that y is related to x by f, so that would be, oh wait a minute, when did I switch to m's and n's? I'm sorry, this should be x's and y's. Oopsie-doo. Nope. Like that. Okay, I'm sorry. Okay, so now we want to show that y is related by f to x, so that would mean that 4 would divide y minus x. So in order to show that, I can say that I can just take the negative of both sides here, so then negative x minus y equals negative 4q. So distributing the negative, what I get is y minus x equals negative 4q. So that tells me that y minus x is divisible by 4 because negative q is an integer. Okay, so I have that y minus x equals 4 times an integer, so that's divisibility by 4. Okay, so that means, or then, y is related by f to x, so f is symmetric. Okay, so that's the symmetric part, and then finally we need transitive. This one is a little bit tricky, but not very tricky. Okay, so we're going to let x, y, and z be elements of the integers, and what we need to show is the following. We will show that if x is related by f to y and y is related by f to z, then x is related by f to z. Okay, so in order to show that, I'm going to go ahead and assume the if part. So assume x is related to y and y is related to z. Okay, so what do I get for that assumption? What does that gain me? That means that 4 divides x minus y, and 4 divides y minus z. Okay? So if 4 divides two numbers, then it should also divide the sum of them. I think that might even be something we proved at some point. Or if you want to go into a little more detail, you could say the following. Then there exist, maybe I'll call them q and r this time, q and r in the integers, such that x minus y equals 4q and y minus z equals 4r. Okay, so that's what it means for x minus y and y minus z to be divisible by 4. It means they equal 4 times some integer. And I just made up the names for the integers. Okay, so then I need to show that x is related to z. In other words, that x minus z is also equal to 4 times some integer. So how you can actually get x minus z to appear from these two equations is just by adding them together. Okay, so I'm just going to add the two equations together. So then x minus y plus y minus z. So I added the left-hand sides equals, and now I'm going to add sorry, I'm writing on top of my PowerPoint controls. This is going to equal the right-hand sides added together. So this is going to be 4q plus 4r, which I can factor to get 4 times q plus r. Okay, so in other words, if I simplify that, what I have is these y's here cancel out. So I have x minus z equals 4 times q plus r, and q plus r is an integer. So this means that 4 divides x minus z. So x is related to z by f. So let me just squish it down in here. F is transitive. And that's it. So that's the whole proof that f is an equivalence relation. Okay, so on the next slide, I will do part 2. Okay, so now let's talk about part 2. So 2, describe the distinct equivalence classes of each relation. So I think I talked about this before, but let's just start with, let's just start with 0, because that's like the middle integer. Okay, so the equivalence class of 0, what you can do is you can actually just add 4s. Okay, so I can start with 0, and then I can add 4, and then I can add 4 again and get 8, and I can add 4 again and get 8. And then if I take the difference between any of these two numbers, I hope you can see that it will be divisible by 4. And I can actually keep going infinitely like that. And then, interestingly, the reason I skipped over all that space is because you can actually do the same in the opposite direction. So you can do -4, -8, and so on and so forth. Okay, so these are all the numbers that are actually divisible by 4, and if you subtract any two of them, it will still be divisible by 4. Okay, so what are some things that we skipped? 1, for example. So let's see, what is congruent to 1 modulo 4? So if I just add 4, then I get 5, and if I add 4 again, I get 9, and then I add 4 again, I get 13, so on and so forth. So if I subtract any two of these, you can just try doing it yourself. You will get something that is divisible by 4. Or another way to think of it is that these are all the numbers whose remainder after long division by 4 is 1. These all have a remainder of 1 if you do long division by 4. And so I can go in the opposite direction here as well, -3, -7, so I'm just subtracting 4s. And I can keep going like that. And then what else have we skipped? We haven't gotten to 2 yet, so let's try 2. So 2 is just going to be the same way. I can add 4, add 4, add 4, and then subtract 4, subtract 4. Okay, and then if you subtract any two of those, the result will be divisible by 4. And then let's try something that we haven't gotten to yet is 3. We did see -3, but not 3. Okay, so 3, if I add 4, add 4, add 4, I get that. And then the opposite direction, subtract 4, subtract 4. Okay, and at this point, if you notice, we've actually covered every integer. Okay, so every integer is in one of these 4 classes, and of course it's not an accident that there's 4 of them. That's because we're doing divisibility by 4. So there's only 4 different remainders that you could get when you do long division by 4. So there are only 4 different equivalence classes. And that's it. Okay, so here is your homework problem. So you have to prove that this is an equivalence relation, and then describe the distinct equivalence classes of the relation. And it's really almost identical to the one I had, except you're using 2's. So go ahead and give that a try. Okay, so let's look at another example here. So I think we had looked at a similar example to this, but we didn't prove that it was an equivalence relation. And I don't think we were using 4, I think we were using 3 or something. But anyway, let me go ahead and prove that this is actually an equivalence relation. So we're working on the set Z of the integers, and so for all pairs m, n in Z, I honestly think these parentheses here are typos. I don't think those should be there. It should just be m and n by themselves. M is related by r to n if and only if 4 divides m squared minus n squared. Okay, so let's go ahead and try. So first I'm going to show that this relation is reflexive. Okay, so I'm just going to and I'm just going to call it x because I'm kind of boring like that. Let x be an element of the integers. And what we need to show, so we will show that x is related to itself by r. Usually this is the easiest one, so let's see, why would this be the case? So if I pluck x in for both m and n, then I get x squared minus x squared, and that is 0, and 0 is divisible by every integer. So I'm just going to say that. Then x squared minus x squared is 0, and 4 does divide 0, so x is related to itself. So that means that this relation is reflexive. Okay, now let's do symmetric. Okay, so now I need 2 elements in my set. So let x and y be elements of Z, and we will show the following. If x is related by r to y, then y is related by r to x. Okay. So I'm trying to show an if-then statement, so I'm going to assume the if part. So assume x is related by r to y. Okay, so I've made an assumption, and where does that get me? So the definition of what I just wrote, the x, r, y part, is the following. then 4 divides x minus y. Okay. All right. Well, I think I'm going to make a little bit different. Oh, I'm sorry. It's squared, right? So then 4 divides x squared minus y squared. Okay, so I think I'm going to make a little bit different argument than I did when I was doing the proofs on the last example. So I'm going to just go a little bit simpler route. Okay, so then y squared minus x squared is just simply negative x squared minus y squared. So 4 should divide y squared minus x squared as well. So I'm not going to bring the actual q's and r's or other integers into it. It should be pretty obvious that if 4 divides any integer, then it also divides the negative of that integer. Okay. I have to say as well. Alright, so I'll go with that argument, and then that means that y is related by r to x. So that means that r is symmetric. Okay. And now let's do transitive. So now I need 3 elements. So let x, y, z be elements of the integers. And we will show the following. We will show if x is related by r to y, and y is related by r, and y is related by r to z, then x is related by r to z as well. Okay, so I'm trying to show an if-then statement, so I'm going to assume the if part. Assume x is related to y, and y is related to z. Okay, so what do I get for those assumptions? What have those assumptions bought me? So using the definition of the R relation, that means that 4 divides x squared minus y squared, and 4 also divides y squared minus z squared. Okay, and I'm going to do a similar argument to the last part, which is a little simpler than what I'd done on the last example. So I'm just going to say that then 4 also divides the sum of x squared minus y squared plus y squared minus z squared. I hope that makes sense to you, that if 4 divides 2 different integers, then it also divides their sum. That's pretty obvious, I think. So these y squareds are going to cancel, so 4 divides x squared minus z squared. Okay, so what does that mean? That means that x is related to z by r, and that means that r is transitive. Okay, so let's do part 2 on the next slide. Okay, so let's look at part 2 here. So for part 2, we're going to describe the distinct equivalence classes of the relation. So this is a relation on all of the integers, so this might be a little bit complicated to figure out, especially since I don't know as much about this relation as about the mod-n relations. But let's give it a try. So I'm just going to start with 0 and try to think about what 0 is related to. So here I'm looking for, obviously 0 is going to be in there, and then I'm looking for other elements where if I do 0 squared minus another number squared, that I get something divisible by 4. So I think if one of m or n is 0, then the other element being even would automatically make it be divisible by 4. Whereas if the other element is odd, I don't think that's going to be divisible by 4. So that's a pretty easy way to figure out that 0 is going to be related to all the even elements. I hope you see why that is the case. Okay, so if I do, for example, like if I do 4 squared, and then I subtract 6 squared, I get 16 minus 36, and then that is 20, or negative 20 rather, and that's divisible by 4, for example. So anytime both of those are even, that should be divisible by 4. Okay. And then I guess for my other equivalence class, I wonder if it is all of the odd integers or not. So let me just try thinking about this. So 1, what would be equivalent to 1 under this relation? Sorry, I just paused the slide and thought about this for a while, but let me actually try to do like a little proof that the other one is just going to be all the odd numbers. So let me write it like this. So proof that m is related to 1 for all odd numbers m. So let's see. So let m be odd. Then m equals 2k plus 1 for some integer k. Okay, and then let's just check whether m is related to 1 by this relation. So then m squared minus 1 squared would be equal to 2k plus 1 squared minus 1. So this will be 4k squared plus 4k plus 1 minus 1. So those are going to cancel. So yeah, you do get something that is divisible by 4. So it's pretty obvious that's divisible by 4 because that's 4 times k squared plus k, and k is an integer. So k squared plus k will be an integer. So I'll just say that since k squared plus k is an integer, for k squared plus 4, or sorry, plus k is divisible by 4. Okay, so this means that m is related to 1 whenever m is odd. So that means for our other, so I'll just stop the proof there. So that means for our other equivalence class, it's going to be all of the odd numbers. So this is going to be, I'll just go, let's see, -3, -1, 1, 3, 5, 7, etc. Okay, so I don't think it's really necessary to do a proof on that part, but I just wanted to really thoroughly check that there were only going to be 2 congruence classes here, or equivalence classes. Okay, so here's your last homework problem. It's extremely similar to the one that I just did, except it's using 3. And that might mean that your equivalence classes are not going to come out quite so neatly. But go ahead and give this a try and check your answers in the back of the book.